Assalamu alaikum. Welcome to another session of Applied Operating Systems, Cyber Defense, and AI Agents. In this particular session, we're going to talk about the Process API from a very good book, Operating Systems, Three Easy Pieces, which corresponds to the fifth chapter of the book. Now, you have a spoon and you have a fork. Now, in this lecture, we'll be covering what is an API. That's a small revision from the earlier lecture. What is the three fundamental system calls: the fork, the wait, and the execute? Why do they matter? And a minor summary. Now, coming back from the previous lecture, we looked at the restaurant analogy to explain what an API is. Now, in this particular example, API is basically the waiter that helps communicate between the kitchen, which is the operating system, and the user here. Now, the user can communicate with the operating system through the menu, which so hence an API is basically a set of tools that helps deliver OS services. The waiter, the different tools on the menu, all are APIs. So, an application programming interface is a collection of tools that are provided to the user to control a system. API works by sharing data, and within OS, all OS related functions are called system calls. Now, these system calls usually run in the kernel mode, which is a privileged mode, and they provide access to the hardware using a privileged access. We're going to talk more about uh, priority levels as well later in the course. Now, going back to the spoon. Now, the fork and the spoon. The fork is interesting because it is a function of, it is a system call of the operating system, and it helps create new processes. In fact, it is called by a parent, which is the existing process, to create a child process. Interestingly, if there's no spoon in a system call, okay, I mean, obviously the picture does show a fork and a spoon giving rise to a spork, but there's no spoon in a system call. But interestingly, a fork does require, in some sense, to spoon feed data into the child process. Now, what really happens? So this is a parent. This is the parent process, and what this parent, and this has its own ID, process ID. Let's say it's 1000. Then what happens here during the execution? A fork call is made. What happens is that the operating system creates within the memory a child process. If the process ID of the parent was 1000, the process idea would be sequentially in order. So it'll be 1001 or 1002, let's say, if some other task was also called in between. But it's going to be the next available number. So so what happens is it's called a nearly identical to the parent because in the sense that it gets its own address space, in the memory, it has its own registers, and it executes independent to the parent. It operates independently. The two processes are independent processes from this point on. You can still connect the parent to the child, but we're going to talk about that later. The child does not start its execution from the main, but rather it starts its execution from the point beyond fork. So if the parent called fork and the program counter says the next instruction is this instruction, here the child is actually going to start from the instruction right after fork. Okay, so let's run the code here for a brief moment. So this is the my Linux frame terminal, and that's the first code. So let's run that. When you run that, you'd see this is the process ID of the parent, and it says, listen, I am the parent, this is my process ID, and I'm the parent of 1649. Notice that the child process ID is one above that of the parent. And this is the child. I am the child, and my RC is equal to 0. So, what is this RC? It is, in fact, the ID of the child of the child. So let's just talk about that for a moment. But notice here the execution. The parent actually finishes execution first, and the child executes later. Let's see if we have the same order in in the code. So if you look at the code is actually here. You can see hello, hello students. That's the process ID, and here the fork is called invoked. Now, once the fork is invoked, if the return child is less than 0, that means here you obtain the process ID. Here, if the return child is less than 0, that means the process didn't create successfully, so you should exit. Now, this is interesting because because this is the point which only executes in the child, and this is the point where this point only runs in the parent. Okay, so notice the return child values for the parent and the child differ, right? So this is fundamentally important because what happens, so if you run this is I ran this previously. So here the child ends after the parent process, even though in the code that you see here, this line of code actually comes after. So what happens is, while the parent receives the process ID of the newly created child, the child receives the return code 0 because the child did not invoke the fork command. It actually the execution of the child actually started after the fork. And this differentiation is useful because that is how you simplify the code writing to handle the parent and child separately. Both processes continue execution independent of the fork, and the child process ends after the parent process. So that means if you go back here, right, when the parent calls in the fork, if the parent has process ID 1000, the child will have a process ID 1001, and the return of the fork to the parent is going to be 1001, indicating that I have a child, the fork process ran successfully, a child was created, and the process ID of the child is 1001. The child execution starts after the fork, so the child command did not execute in the fork. Because the child command did not execute in the fork, the child's return child is 0 because it didn't really create any children. The child didn't create any children. That's why the return child is equal to 0 is true for the child, but it is not true for the parent. Because for the parent, the return child is the value of the process ID of the child. So that's how you can create children blocks of code that run for the child and blocks of code that run exclusively for the parent, giving each of them their own characteristic and quality. Now, because the child ran first, sorry, the parent ended their because they continue their execution independently. The parent actually finished its execution first, and the child only finished it later. So, what if you want to wait? What if the parent wants to wait for the child to finish his execution? Well, it's simple. You just call the function wait. So now you add another include statement here. The rest of the code is the same. You get the process ID, you check if the fork command executed successfully. If not, you exit. And if it did, the parent is going to get the process ID of the child. Obviously, the child did not invoke fork. So for the child, the return child is 0. Now for the parent, here you add one additional statement, which is I want to wait for my child to finish execution before I run this command. So now what happens is, while the parent is running, while the parent process is running, let me run the code here just to show you. So this is going to be I think 5b. Right. So here you see, now here you see the child actually completes its execution first, and then the parent finishes its execution. This is common to both. Now, in this book, if you look at the code here, what happens is the code is largely the same. What happens here is the parent, when it calls, so the program, the parent process is already in the CPU, it's running. Now, when the code is running, the fork, a child process is made, the parent is still running, and it comes to this point where the wait command is invoked. Now, what the wait does, it actually deschedules the process and blocks it. The parent process gets blocked. Remember, in the first lecture, we discussed there are three states of a process: it's either running, or it's ready, or it's blocked. A process is blocked when it's waiting for an event to occur. In this particular instance, the process is waiting for the child to finish execution. So now, once the child, so the parent process is blocked, and when the child process is brought from the ready state to the running state, it runs, it completes its execution. When the child process completes its execution, the OS tells the parent process, listen, I have completed finishing the execution of the child. Now you can be ready for execution. So basically it brings back the parent process from the block state to the ready state, and whenever it's time to run, it runs. And that's why you now see that this particular command finishes after the child has completed its execution. Okay. Now, beyond that point, here's another important. Okay. So here's another interesting command. It's called the word count, and it's a tool present in Linux. What it does, it returns the word count of a file. This is the output given. Let's say a program. It requires a program as it requires a file as an input. So you can see it returns the first number, returns the number of lines present in p3.c. The second indicates the number of words present in p3.c. The third indicates the number of characters, and the fourth is the file name itself. So the last important command is the system call is the execute. Now, what the execute does, it helps run another program altogether. So it doesn't actually create a new program. The process ID remains the same. Again, the process ID remains the same. Instead, what it does, it replaces the current running of the program with the code and the static data of the new program. Okay. The process is allocated memory, that is the code, stack, heap, uh, static data. They're all overwritten, and the new program runs over the old process. So let's run this code. So for instance, here, if I run code this, you would see here it says hello world, hello, I am the child, and then it gives you the number of lines in this particular code, the number of words, the number of characters, and then the parent ends. If you want to look at the code here, so you have this is your code. These are the fundamental include statements. Here it's the hello world and the process ID of the parent. And then you create a child process. You check if the child process worked or not. In this case, it did. And then it says here, hello, I am the child. As you can see here, hello, I am the child. And then notice that this command runs I mean, if I was to run this command here, let's say, and give it chapter 5b dot c, I get the same output: 31 lines of code, 103 words, 809 characters of this. So, what happened? So, what happened here, you're going to pass on, you're going to run the execute VP, which is a variation of the execute command system call. So you're going to call this system call, and you're giving it first the argument. You're going to tell it specifically which command you're going to run. In this case, it's word count, and then the whole command, basically wc com space chapter 5b dot c. Okay, actually I changed this, so I'm gonna replace this with wc, and yeah, wc, and then I'm gonna replace it, the program file you want to check, file you want to count. Yes. And when you pass this, what happens is you notice that this particular line never actually runs. You never see execute failed. What happens is the entire assembly code, the entire, everything in the, what happens is the entire memory of the child process, the process ID of the child remains the same, but the entire whatever was in the code segment of the memory, the data, the heap, everything was rewritten by this particular command. It replaces the child's program entirely, and it runs. The parent obviously still waits for the child because the process ID is the same. So the parent waits. When the child finishes execution, it continues its execution. Okay. And that's what we saw here. The parent ran after the child completed its execution. So there are 6 variations of execute. We used this particular one, but there are others as well. So here in this particular lecture, we basically learned 3 APIs in the Linux, which are key system calls. The first is the fork that helps creates a child process, a copy of the parent whose execution starts from fork onwards. Then we looked at the wait, which was needed because you sometimes want the parents need to wait for the child to finish, depending on what the child does. And the last system call, which is execute, which completely replaces the current process with the new one. And you can tell specifically which process is required. Here it was word count. You can try multiple system, you can try multiple tools, like you can just say ls, which is just list me all the files in the drive, and you can basically do whatever you want. Okay, hope that helps. Until next time, thank you very much. If you have any questions, you can drop them in the comments and I'll try responding to them. A lot of times you would see that, those questions will actually continue coming in the lectures to come. Thank you very much. Bye bye.